welcome back to Sky Creative Channel. From molten steel to massive offshore structures, join us as we explore 6 world-class metalworking operations that are keeping industrial traditions alive with cutting-edge technology. Let's get started. We're taking you inside Sarstal Askoval, a pioneering steelmaker that's rewriting the rulebook on how we produce steel in the 21st century. Now, if you remember the old days of steel production, those massive blast furnaces that defined American industrial might in Pittsburgh and Gary, Indiana, you'll appreciate how far we've come with what they call green steel. At Sarstal Askoval's facility, the heart of the operation is the electric arc furnace, or EAF. Think of it as a giant electric crucible that reaches temperatures around 3,000 degrees Fahrenheit. Instead of using coal and iron ore like the traditional blast furnaces many of us grew up knowing, this modern marvel melts down scrap steel using powerful electric arcs. Imagine lightning captured and put to work. 3 massive graphite electrodes, each about the diameter of a telephone pole, descend into the furnace and create an electrical arc that generates incredible heat. It's fascinating how they've turned electricity into the primary heat source, making the process cleaner and more sustainable. NTHE scrap steel gets loaded into the furnace through a charging system, typically by overhead cranes dropping large buckets of material. Once the furnace fires up, those electrodes create arcs that jump between them and the metal charge, melting everything into a glowing liquid pool. The operators carefully monitor the chemistry, adding alloys and flux materials to achieve the precise steel grade required. This whole melting cycle takes about 45 to 90 minutes, depending on the heat size. Here's where it gets really interesting. Once the steel reaches the right temperature and composition, typically checked using sophisticated computerized systems that would have seemed like science fiction back in the 1970s, it gets tapped from the furnace into a massive ladle. This isn't your grandpa's bucket. We're talking about refractory-lined vessels that can hold 100 tons or more of molten steel at temperatures that would vaporize most materials instantly. And from there, the liquid steel moves to the continuous casting machine. Now, this technology revolutionized steelmaking when it emerged in the 1950s and 60s, and it's still the backbone of modern production. The molten steel pours into a water-cooled copper mold, either rectangular for slabs and billets or circular for rounds and blooms. As the steel enters the mold, it begins to solidify from the outside in, forming a thin shell. The brilliant part? The steel doesn't stop. It keeps moving downward through the machine while water spray systems cool it progressively. Rollers guide the solidifying steel through multiple cooling zones, and by the time it exits at the bottom, you've got a continuous strand of solid steel, still glowing red hot but firm enough to be cut by powerful torch systems into predetermined lengths. It's like watching industrial magic happen in real time, turning liquid metal into solid billets, rounds, or blooms ready for further processing. This entire operation represents the cutting edge of sustainable steelmaking, proving that American know-how and innovation aren't just about the past, they're shaping our industrial future. Now let's visit Stalcon, a company that represents the kind of precision metalworking that built America's industrial backbone. These folks specialize in fabricating and assembling steel structures for specialized cranes and ship loaders, the kind of heavy-duty equipment that keeps our ports and industrial facilities running smoothly. If you've ever watched cargo ships being loaded at a major port, you've seen their handiwork in action. And Stalcon's operation is a masterclass in what we call structural steel fabrication, and it all starts with engineering. Before a single piece of steel gets cut, their design team creates detailed 3D models and fabrication drawings. This is worlds away from the blueprint tables some of us remember. Today's engineers use sophisticated CAD software that calculates loads, stresses, and exact dimensions down to the millimeter. These digital models feed directly into their fabrication equipment, ensuring precision that was simply impossible in the old days of manual layout work. NTHE raw material arrives as structural steel sections, I-beams, channels, angle iron, and heavy plate steel. The first major operation is cutting and preparation. Stalcon employs several cutting technologies depending on the application. For straight cuts on beams and plate, they use automated bandsaws and shearing machines. But the real showstopper is their CNC plasma and oxy-fuel cutting tables. These computer-controlled torches follow the digital patterns from those engineering files, cutting intricate shapes and connection details into thick steel plate. The cutting head moves in 3 dimensions with remarkable accuracy, while the torch itself cuts through steel up to several inches thick, using either a superheated plasma arc or an oxygen fuel flame that literally burns through the metal. It's like watching a hot knife through butter, except the butter is half-inch steel plate. And once the pieces are cut, they move to the preparation stations where workers use grinders to bevel edges for welding, drill bolt holes with magnetic drill presses, and clean the surfaces. This prep work is crucial. Good welds and proper fit-up depend on it. Many of these techniques will be familiar to welders from the 1960s and 70s, though the tools have certainly improved. NTHE assembly process is where things get really interesting. For crane structures and shiploader components, we're talking about massive assemblies that must fit together with incredible precision. Stockon uses heavy-duty welding fixtures and jigs, essentially custom-built frames that hold components in exact position during welding. Their welders, many certified to the highest international standards, use multiple welding processes. MIG welding handles much of the production work, feeding wire electrode continuously for fast, efficient joining. For critical, structural connections requiring deeper penetration, they employ flux-cored arc welding or even submerged arc welding, where the arc burns beneath a blanket of granular flux, creating exceptionally strong welds. Overhead gantry cranes, some capable of lifting 50 tons or more, move these massive assemblies through the shop. Watch closely and you'll see the careful choreography. Components being positioned, tack welded to hold them in place, then finish welded in specific sequences to minimize distortion from welding heat. After welding, structures often go through stress-relieving processes and dimensional checks using laser measurement systems. NTHE final stages include surface preparation by shot blasting, propelling steel shot at high velocity to clean and profile the surface, followed by protective coating application. Many structures get a multi-layer paint system, primer, intermediate coat, and finish coat, all applied in controlled environments. The result is structural steelwork that'll withstand decades of harsh service in marine and industrial environments, carrying on the tradition of quality American metalworking into the modern era. Folks, what we're about to explore is truly one of the engineering marvels of our time, the fabrication and installation of the Valamone jacket by Herma Fabrication Group for Statoil. Now, if you're not familiar with offshore oil and gas production, a jacket is essentially a massive steel tower, built like a giant erector set, that sits on the ocean floor and supports the production platform up top. The Valamone jacket is particularly impressive because it was designed to operate in the challenging waters of the Norwegian North Sea, one of the harshest marine environments on Earth. NTHE's story begins at Herma's Vlissingen facility in the Netherlands, a fabrication yard that's been building offshore structures since the days when offshore drilling was in its infancy back in the 1960s. The scale of this operation is hard to grasp until you see it. We're talking about a steel structure that stands over 100 meters tall and weighs thousands of tons. Imagine the Statue of Liberty, but made entirely of heavy tubular steel and designed to withstand 100-foot waves and brutal North Sea storms. NTHE fabrication process starts with engineering and planning that takes years. Every connection, every weld, every structural member is calculated and analyzed using advanced computer modeling. The jacket consists primarily of large diameter tubular sections, steel pipes ranging from 1 to 3 meters in diameter with wall thicknesses that can exceed 100 millimeters. These aren't your standard pipes. They're specially manufactured for offshore use, made from high-strength steel that maintains its toughness even in frigid waters. Not Vlissingen, the work begins with the main legs, the 4 massive vertical columns that form the jacket's corners. These legs are fabricated from rolled steel plate that's been formed into cylinders and seam welded. The facility uses specialized plate rolling equipment that can handle steel sections weighing many tons. Once formed, these cylinders are welded together to create legs extending hundreds of feet in length. The welding process is absolutely critical here. Hirema employs certified welders using submerged arc welding for the longitudinal seams, a process where multiple welding heads run simultaneously along the joint, with the arc burning beneath a blanket of granular flux. This creates deep penetration welds that are radiographically tested to ensure they're absolutely perfect. Remember, these welds will be underwater for decades, supporting enormous loads in one of the world's most corrosive environments. And between the main legs, fabricators install a complex network of diagonal bracing, horizontal sections, and additional structural members. This is done using massive fabrication jigs, essentially custom steel frameworks that hold everything in precise position. The facility's heavy lift cranes, including specialized gantry cranes with capacities exceeding 1,000 tons, position these enormous tubular sections while welders make the connections. Each connection point, or node, is an engineering challenge itself. Where multiple tubular members meet at angles, special connection pieces called cans are fabricated. These are complex three-dimensional steel shapes, often formed by cutting and fitting heavy plate steel, then welding it all together to create a joint that can transfer millions of pounds of force. Throughout fabrication, quality control is paramount. Every weld undergoes non-destructive testing, ultrasonic examination that uses sound waves to detect any internal flaws, and radiography where X-rays or gamma rays create images showing the weld's internal structure. Dimensional control is equally critical, with laser measurement systems constantly checking that everything aligns within tolerances measured in millimeters across structures stretching hundreds of feet. And once major sections are complete, they receive protective coatings. The jacket is shot blasted to remove mill scale and contamination, then painted with specialized marine coatings. Typically a multi-layer system including zinc-rich primer, epoxy intermediate coats, and polyurethane top coats. These coatings must last decades underwater without maintenance, protecting the steel from the North Sea's corrosive saltwater. NTHE installation phase is where Hirema's specialized expertise truly shines. The jacket is loaded onto one of their heavy lift vessels, ships equipped with massive cranes that can lift weights that would be impossible for land-based equipment. The journey to the offshore location is carefully planned around weather windows. Once on site, the jacket is lifted from the vessel and lowered through the water column to the seabed. Guide frames and specialized positioning equipment ensure it lands exactly where intended. Once positioned, piles are driven through sleeves in the jacket's legs deep into the seabed. We're talking about steel piles, 150 feet long or more, driven by massive hydraulic hammers that deliver blows with millions of foot-pounds of energy. These piles anchor the jacket permanently in place, and grout is pumped into the annular space between pile and sleeve, locking everything together. The precision required is astounding, achieving tolerances of inches across a structure hundreds of feet tall, working in waters hundreds of feet deep, often in challenging weather. It's the kind of engineering achievement that rivals anything from the golden age of American construction, updated with 21st century technology and know-how. This is heavy industry at its finest, folks. Let's turn our attention to ASO Siderurgica, a company that represents the continuing evolution of steel production. While they employ modern techniques, there's something beautifully traditional about watching molten steel flow through their facility. It connects us to over a century of metallurgical heritage. NASO's process begins with their melting operation, typically using electric arc furnaces similar to what we saw at Saarstahl. They charge the furnace with carefully selected scrap steel and alloying elements. Then, those powerful electrodes strike their arcs, generating temperatures that would melt stone. The operators monitor the melt chemistry through computerized systems, while also relying on the kind of practical experience that takes years to develop, knowing how the steel behaves by its color, by the way it flows, even by sound. Once refined to specification, the molten steel is tapped into ladles, where secondary metallurgy takes place. This is where they fine-tune the steel's properties, adding precise amounts of alloys like manganese for strength, silicon for deoxidation, and other elements depending on the final product requirements. From there, the steel proceeds to casting. Depending on their product mix, ASO might use continuous casting to produce billets or blooms, or alternatively pour into ingot molds for certain specialty products. The continuous casting process features those water-cooled molds we discussed earlier, with the steel solidifying progressively as it moves through the machine. The finished products, whether billets, blooms, or ingots, move on to their next destination, perhaps a rolling mill or forging operation, carrying forward steel's essential role in building our modern world. Now we visit ISACSRL, specialists in stamping and machining operations for steel products. This is the kind of precision metalworking that transforms raw steel into the countless components modern industry depends on. If you've ever wondered how your car's body panels get their shape or how steel enclosures for machinery are formed, you're about to find out. NTHE heart of ISAC's operation is their stamping presses, massive machines that use tremendous force to shape steel. These hydraulic and mechanical presses range from smaller units exerting 50 tons of force up to monsters capable of 500 tons or more. The steel arrives as sheet or coil stock, typically cold-rolled steel with thickness from paper thin up to quarter-inch or more. It's fed into the press, positioned precisely by feed systems. Then, wham, the upper die descends with controlled force, meeting the lower die and forming the metal into shape. Modern presses cycle rapidly, some making 60 strokes per minute, each one perfectly repeating the operation thanks to computer controls. NTHE tooling itself is fascinating. Each die set is custom-made for specific parts, machined from hardened tool steel that can withstand millions of cycles. For complex parts, they use progressive dies. The steel strip advances through multiple stations, each performing a different operation, piercing holes, bending flanges, forming curves until the finished part emerges at the end. It's like an assembly line compressed into one tool. NISAC also employs various forming operations. Their press brakes use precision-controlled hydraulic rams and segmented punches to bend sheet metal to exact angles. CNC turret presses punch patterns of holes at high speed, the turret rotating to select different punch and die combinations automatically. After forming, many parts proceed to machining centers, where CNC mills and lathes add precise features: threaded holes, mounting bosses, tight tolerance surfaces. The integration of stamping and machining under one roof represents efficient modern manufacturing, turning flat steel into finished components with remarkable precision and repeatability. Our final stop takes us to International Pipe Industry Company, known as IPIC, where they fabricate large steel structures and piping systems for industrial applications. This company represents the kind of heavy fabrication that built the infrastructure of the modern world. Power plants, refineries, chemical plants, and major industrial facilities all depend on companies like IPIC. NIPIC's specialty is working with large diameter pipe and heavy structural steel, creating assemblies that must withstand high pressures, extreme temperatures, and decades of service. The process begins with their material receiving area, where structural steel sections and pipe arrive from steel mills. We're talking about pipe ranging from several inches to several feet in diameter, with wall thicknesses that can exceed 2 inches for high-pressure applications. The steel itself is specified to exacting standards, different grades for different services, with properties carefully controlled during manufacturing. NTHE fabrication floor is equipped with specialized machinery that would impress any metalworker. For pipe work, they employ beveling machines that prepare pipe ends for welding. The pipe rotates in a chuck, while carbide cutting tools machine a precise bevel angle, typically 37.5 degrees for most applications, creating the groove geometry needed for full penetration welds. Modern beveling machines are CNC controlled, ensuring consistent preparation whether the pipe is 6 inches or 60 inches in diameter. End cutting operations use multiple technologies. Bandsaws handle smaller structural sections, but for large pipe and heavy plate, they turn to plasma and oxy-fuel cutting. Their CNC cutting systems can handle pipe up to several feet in diameter, rotating it while the torch follows a programmed path, cutting complex copes and miters that allow pieces to fit together perfectly. An assembly is where experience meets technology. IPIC uses extensive fixturing systems, custom welding jigs, and positioners that hold components in precise alignment. For pipe assemblies, they employ pipe rollers and turning rolls that rotate the pipe during welding, allowing welders to work in the flat position where quality is easiest to achieve. Their welding operations are impressive in scope. For critical pressure piping, they use gas tungsten arc welding, GTAG, or TIG, for root passes, the first weld layer that fuses the pipe sections together. This process uses a non-consumable tungsten electrode and separate filler rod, producing exceptionally clean, high-quality welds. Following the root pass, they switch to shielded metal arc welding, stick welding, or flux cord arc welding for fill and cap passes, building up the joint to full strength. NFOR structural components, they employ metal inert gas, MIG welding, and flux cord processes, chosen for their high deposition rates and good mechanical properties. The fabrication of large structural assemblies requires careful sequence planning. Welding creates heat that can distort the steel, so experienced fabricators know to weld in patterns that balance and control distortion. They also use strongbacks and restraints to hold assemblies in place until welding is complete and the steel has cooled. NNSUR face preparation and coating follows fabrication. Shot blasting removes mill scale and creates the surface profile necessary for coating adhesion. Depending on the service environment, they apply various protective systems, from simple alkyd enamels for indoor structural steel to sophisticated multi-layer epoxy and polyurethane systems for corrosive environments. Some pipe systems receive internal coatings or linings for chemical resistance. NTHE final products are impressive: complete pipe spools ready for field installation, structural modules weighing many tons, pre-assembled systems that arrive at job sites ready to bolt together and commission. IPIC's work represents the continuation of industrial fabrication traditions, stretching back generations, updated with modern technology but still dependent on skilled tradespeople who understand their materials and take pride in their craft. It's heavy industry at its best, folks,